Hello everyone. My name is Sanya Singh and I'm a student of first SEM CSE in Sri Venkateshwara College of Engineering. And my topic is matter waves and their properties. This is an overview of the topic that we will be covering today. I will be talking about matter waves properties in detail. So let's begin with the introduction of matter waves. In quantum mechanics, matter waves are a fundamental concept that describes the wave-like nature of particles such as electrons, protons, and atoms. Matter waves play a central role in quantum mechanics, offering a wave-like description of particles and fundamentally altering our understanding of the physical world. The Schrödinger equation and the associated wave function provide a powerful framework for explaining the behaviors of particles in the quantum realm. Wave-particle duality. The wave-particle duality is a fundamental concept in quantum mechanics that describes the dual nature of particles. It suggests that particles such as electrons and photons can exhibit both wave-like nature and particle-like properties under different experimental conditions. Now, let's understand de Broglie wavelength. The de Broglie wavelength lambda is related to the momentum of a particle through the de Broglie wavelength formula, where lambda is equals to h by p. Lambda is the de Broglie wavelength, h is Planck's constant, which is 6.626 into 10 to the power minus 34, and p is the momentum of the particle. Now, let us understand the topic Schrödinger equation. The Schrödinger equation is a fundamental equation in quantum mechanics that describes how the quantum state of a physical system changes over time. The time-independent Schrödinger equation for a single non-relativistic particle is given below. Here, in this formula, I is the imaginary unit, h is the reduced Planck's constant, Dou phi by dou t is the partial derivative of the wave function with respect to time, and capital H is the Hamiltonian operator representing the total energy of the system. Probability density. In quantum mechanics, matter waves are associated with the probability density through the concept of wave functions. In this, we have wave functions and probability amplitude. In quantum mechanics, the state of a particle is described by a mathematical function known as the wave function, which is often denoted as psi. Measurement and collapse. When a measurement is made, the wave function collapses to a specific state corresponding to the observed outcome. Next, we have phase velocity. Superposition principle. Quantum systems can exist in a superposition of multiple states simultaneously. The wave function reflects the superposition. Normalization condition. To ensure that the probability of finding the particle somewhere in space is 100%, the wave function must satisfy the normalization condition. Wave function and probability amplitude. In quantum mechanics, the state of a particle is described by a mathematical function, which is often denoted as psi. Uncertainty principle. The matter waves is connected to the Heisenberg's principle. Moving on to our next concept, wave packet. A wave packet is a concept in quantum mechanics that represents a localized and typically short-lived disturbance in a wave field. It is used to describe the localization of a particle in both position and momentum space. It arises from the superposition of different momentum states leading to interference patterns that can be adjusted to create a well-localized and time-evolving probability distribution for the particle's position. The concept of wave particle is crucial for understanding the probabilistic and wave-like nature of particles in quantum mechanics. Group velocity. The group velocity is also represented as Vg, is defined as the velocity of the maximum of the envelope of a wave packet. For a monochromatic wave, the group velocity is same as the phase velocity. However, for wave packets composed of multiple frequencies or modes, the group velocity can differ from the phase velocity. Mathematically, the group velocity can be expressed as the derivative of the angular frequency with respect to wave number. Here, omega is the angular frequency and k is the wave number. Next, we have quantum tunneling. Quantum tunneling is a fascinating phenomenon in quantum mechanics that arises from the wave-like nature of particles. It occurs when particles, such as electrons, exhibit the ability to pass through a potential energy barrier that classical physics would predict to be impenetrable. Quantum mechanical tunneling examples include alpha decay, scanning tunneling microscopy, and nuclear fission in stars. So here is a diagrammatic representation of quantum tunneling. So this is a very simple diagram which represents how quantum tunneling exactly works. So here are some of the applications of matter waves. First up, we have quantum computers. Quantum computers use qubits which can exist in multiple states simultaneously due to superposition. This superposition is represented by matter waves. Quantum gates manipulate these matter waves to perform operations on qubits, allowing quantum computers to process information in parallel. Another quantum phenomenon related to matter waves, which that is enables qubits to be correlated in a way that state of one qubit is dependent on the state of another. Next, we have electron microscopy. In electron microscopy, matter waves, especially when electron waves, are utilized to overcome the limitations of traditional light microscopy. Electrons have much shorter wavelengths than visible light, allowing for high resolution in imaging. Last, we have MRI. MRI relies on the behavior of atomic nuclei in a magnetic field. To conclude it, the profound impact of matter waves lies in the transformative influence on our understanding of quantum mechanics. From the conceptualization of particles as both wave and particles to the development of Schrödinger equation, matter waves have fundamentally altered our view to the quantum realm, leading to the groundbreaking applications and technologies that continue to shape the future of science and technology. Thank you for watching.